There we go. All right, so today we're starting the review chapter. It's R1 and R2 in the book. R1 is on set notation. This is the section I like the least. This is the section you're going to use the least, but I still need to cover it. So let's go Math 35. R1 is on set notation. So a set is a collection of objects. Objects in the set are called elements or members. Elements is the one they tend to use the most. And another fun thing to know is we identify sets using curly braces. Order is not important. Set 1, 2, 3 is the same set as 3, 2, 1. If we're identifying members of a set, we will use this symbol. This means is an element of. And if we cross this shit off, is not an element of. I'll give an example in a second. One is an element of 1, 2, 3. 4 is not an element of 1, 2, 3. And it may be obvious, you may go, no shit, I can see that it's not an element. I can see whether it's in it or not. Where this comes in handy is sometimes sets are really, really big. So we tend to identify sets with letters. Or label them with capital letters. Say set S is 1, 2, 3, 4, 5. Sets can be finite or infinite. I wish they said infinite, because Infinite is the opposite of finite, but they don't sound like the opposites. They sound like different words entirely. Finite set has a countable number of terms of elements. Like S. S is a finite set here. So that's finite. Infinite sets are uncountable. For example, the set of natural numbers they tend to identify with an N, and it's got a double bar for the first thing, makes it pop. N starts with 1, goes to 2, goes to 3, and it keeps going. Where these are called, this is called the ellipses. And it means keep following the pattern without end. Forever. So the pattern here is each number is going up by 1. So the next number will go up by 1, 3 goes up to 4, 4 goes up to 5, so on and so forth. So the set of natural numbers is infinite. There is no final number. Get through this section pretty quickly. Most of the section today is on R3a. Let's see, some other stuff you will need to know. You'll see it. I'm not testing you on this shit, but you need to know it because when you see it, you need to go, what the hell does that mean? Set builder notation. And then give an example and then spell out what it means for you. So the first part is the set of all elements X. And X here is a variable or a placeholder. The vertical bar means such that. And the right side is exactly what it says. So it's the set of all elements X such that X is a fraction between 0 and 1. So like 1/2 is in there, 1/3, 1/4. I could keep going with numbers along the bottom and just leave them the same, but it also includes shit like 2/3. 5 sevens. I'm not gonna use dots. Because there's no pattern here. And hiccups. Every once in a while, you see this pop up in that, like, homework in the book and shit. There is some terminology that ends up being useful later on. Anyone need this up longer? If you do, say so now, or wait for it to be uploaded later. All right, so another letter that's used a lot, U, is the universal set. And this contains all elements applicable to a specific situation. I remember we said sets are objects, so these don't have to be numbers. We're talking about like a deck of cards. The universal set has 52 elements. There's 52 cards in a deck. Sure, some of them have numbers on them, but some of them don't, and they've got symbols on them and shit like that, hearts and diamonds and stuff like that. It just means there's a collection of them. There is the null set or empty set. Wow, what the fuck, set or empty set? There is nothing in it. Not even 0. It's just a set of empty braces. Now you can write it as that, or you can write it as that. Those are two valid ways of showing the null set or empty set. But don't do this. Don't put one in the other. Some other terminology, subsets. Are completely contained in other sets. What sets did I just use? I used the set S and N. I used S and N. So recall S was 1, 2, 3, 4, 5. N is 1, 2, 3, and it keeps going. The way we denote subset, is we use this symbol for subset. So S is a subset of N. Going the other way, N is not a subset of S. So we just do that vertical bar thing again, or that diagonal slash diagonal. It's not really vertical, it's diagonal. This seems kind of stupid, but a set is always a subset of itself. If you go far enough along the stem sequence, like in the linear algebra, this shit actually becomes important when you start talking about what makes a linear space or a space. And then the null set. The null set is a subset of every set. You can get rid of S and literally just put every set. Yes.
Would because S is a subset of itself, would N also be a subset of itself?
N is a subset of itself, yes. Venn diagrams. Let's do some Venn diagrams. So we've already used S and N. I'm going to add in another term for the Venn diagram. I'm going to make my universal set be all numbers. It's all numbers. Rational, irrational, complex, integers. Is all numbers. U is going to be all numbers. So we already said S was a subset of N. And the natural numbers are a subset of all real numbers. So pictorially, what that means in the Venn diagram is we tend to make the box, like we draw a box just to describe the whole space. We'll call that U as the big space. And we'll pick a region in there to define N. This will be N. And inside of N is S. So what if I defined, well, we have N already. The complement of N we're going to do N with an apostrophe. It's pronounced N prime. And complement is everything in the universal set that is not an N. Sometimes you'll see a C up there instead of the prime. C for complement. So if N is this blue circle. N prime is like everything outside the blue circle. In Venn diagram wise. Ready for more? Okay, let's come up with two new sets real quick, A and B, just to illustrate the last few properties. The ones that actually are useful. Let's call a set A is going to be 1, 2, 3, and 4. Let's say set B is 3, 4, 5, and 6. Those are my two. Whoops. There was shit off. Those are my two sets. All right, so the first thing we're going to talk about is like the overlap. So all elements that are in both or like overlap are represented by the intersection symbol. Which is a upside down, kind of wide capital U. And the way we use it, we say A intersects B. And what elements are in both? Just 3 and 4, right? So they'll say where A intersects B. But another way of looking at it is in A and in B. It has to be in both. This will matter when we're talking about domains and some good shit like that. This symbol, the intersect symbol, comes back up. As does its sister. The other one we use is, so if we want to look at all the elements in either of them, A or B. Here we use, it's called the union symbol. And it's a capital U, but it's helpful to kind of make it like a wide capital U, like wider than you would make a regular U. So that you go, nope, that's not a U. So in our example, if I do A and then union, oops, that should be a U, the union symbol, not a U. A union B. It's gonna be all the numbers that are in either of them. So we've got 1, 2, 3, 4 in A. And the numbers that are in B that aren't already listed are 5 and 6. We don't have to list 3 and 4 again because we already have it. So this is what they say is the union of A and B. I think an easier way to think of it is it's in A or in B. So as long as the number is in either A or in either B, we'll use that. So this is A and this is B, and I've got 1, 2, 3, 4, 5, 6. This 3, 4. That's my A intersect B. And A union B would be everything that's in this area. I'm going to shade it well. Everything that's in both of them. Are we having fun yet? This is the best shit ever, right? I don't even like this part. Venn diagrams aren't too bad. They're actually useful in situations. But the talk of sets and all that, this is tedious. But I have to do it. It's part of the rules. I don't make the rule. Well, I do make the rules, but I don't make all the rules. Unintentional. All right, you guys ready for the next section, R2? This page, that was page 3. R2 is on real numbers and their properties. This is fun. Just to show you what the R symbol looks like for set notation. R, which is the real numbers, is the all elements X such that X is a point on the number line. How is that for the most useless definition ever? If I make a line and I put numbers on it, any number that exists is on that line. So other major sets of numbers is, we already talked about n. N is the natural set. It's 1, 2, 3, and keep going. For the natural numbers. The whole numbers are almost exactly n, except they have one more value. Whole numbers have 0 in them. And other than that, they look just like n. I don't know what letter they use for whole. W maybe? Maybe W, who fucking knows? Who cares? Integers are next. Integers like have, I'll do dots on the left to show it keeps going to the left, but it's all the whole numbers and negative numbers too. Then we have the rational numbers. The official definition is P over Q such that P and Q are integers. Q does not equal 0. So like this is all your fractions. And integers. Because P and Q can be the same, it doesn't say P and Q can't be the same number, so like 3 over 3 is 1. Negative 6 over 3 is negative 2. It's an integer. But it's also a rational number. And then the final category that's in the real number set is the irrational numbers. And this is the worst definition ever, even worse than R. This is X such that X is an element of R, but X is not an element of the rational numbers. So this is, you got your symbols that you've seen before. Pi is in here. E is in here. All your square roots tend to be in here, except the ones that make like perfect square, like square root of 2 is an irrational number. Square root of 5 is an irrational number. These are just examples. Decimals that don't repeat and don't end. Like pi and e, and root 2 and root 5. We want to do a Venn diagram of this bad boy. Over here, I'm just going to slap my irrational numbers. I'm not going to use circles. This entire box is R. Then if that's the irrational side, everything else is the rational side. That'll be the rest of the numbers over here. The rest of the numbers over here are rational. Inside the rational numbers, we have integers. Inside the integers, we have whole numbers. And inside the whole numbers, we have natural numbers. So these are all subsets of a bigger set. And R is not the biggest set of numbers. It's the biggest set of real numbers. We will be hitting complex numbers at some point in the semester, the I. Remember ever seeing it in high school? All right, who's tired of that set shit? Let's go over some algebra. You have a chance to finish writing that, and the show goes on. Well, this page one, two different sections for our one. Anyone need this up longer? All righty. All right, algebraic expressions. They combine numbers and variables. Through basic operations. Like plus, minus, multiply, divide. Exponents. Roots, which are exponents, but we haven't gotten to that yet. Those are algebraic expressions. Some of those are called exponential expressions. They have an exponent in them. Like 2 cubed is 2 times 2 times 2, which is 8. The number on bottom is called the base. The number on top is called the exponent. You will also see these called exponentials without the term expressions. So a generic form. We got like a to the n power. This is really just a times, and you keep doing a bunch of a's. And if you count up all the a's, there are n number of a's multiplied together. terminology that is used with it. This is a to the nth power. It's how we verbally say exponents. And some folks, I am guilty of this, sometimes drop the power part, a to the n. It's just lazy, really. Oh, fuck, it's too early to be yawning. Right?
Why are you looking at me when you say that?
I just looked at, you were the last one I looked at, you just happened to look up right when I was looking at you. I bet someone else in here is trying to sleep already and it's rubbing off on me. That's what it is, I'm blaming it on that, stupid. All right, so, we said it's through basic operations. What do we do with those basic operations? We follow the order of operations. PEMDAS. These represent operations. P is for parentheses. This includes other grouping symbols, which could be like brackets. You can see curly braces in it, even though we said it's used for sets. When you got enough fucking parentheses, you get tired of using, it's hard to tell which parentheses for which. So it's nice to change it out with like brackets and curly braces. Absolute value bars, that falls in that category. Radical signs break things up, that's a grouping thing. And like a fraction bar. Those all count as parentheses or grouping things. So P is really like a G might be a better word, but and I've seen some teach it with a G. I'm not going to because I like my phrase that I use with it. E is for exponentials. These are the orders we do things in, and we'll do them in a second. I'm sure you've all seen these before at some point, whether you remember it or not. M is multiplication, D is division, A is addition, and S is subtraction. So M and D, as well as A and S separately, within these two little like box area things I've got going on, they have the same priority. So we just go left to right. We'll do all the multiplication and division at the same time, just going left to right. Then we do all the addition and subtraction going left to right. Now, what a lot of teachers teach this, and a lot of books teach this, the mnemonic to remember it. Please excuse my dear Aunt Sally. That's the memory thing to remember, PEMDAS. That is not what I use. Does anyone in here have an Aunt Sally? How absolutely fucking useless is this phrase then? How many of you have a brother or a sister? Please excuse my dumb ass sibling. Now, if you don't have any brothers and sisters, you'll have to find your own S. Someone told me yesterday I should use students, but that's not correct. Everybody that has a family, you think your brother or sister, well, at least one of them is a dumbass. If you don't, they think you are, so maybe you're the dumbass in the group. But that's easy to remember, and that applies to me. My brother's a dumb shit. I'll have to figure out a way to add shithead in there instead of someone. No, my brother, he's a plumber. He did not go to college. Went to like plumber training. He makes almost, I think he makes as much as me. He was making more than me for a while, and now I'm like, hey. But I had to do what fucking bachelor's degree and graduate degree, and he went and just did training for fucking 6 months and did on the job work forever. Does anybody need that up longer? Let's do some practice with it. Or do you guys want a 5-minute break? What? Let's take a 5-minute break. All it takes is one person to say they want a break, and we'll take a break. Because if you have it my way, you'll be working here till 11:30 at night. Which is completely false. Gotta go home and find a fucking ruler tonight. I know I got 2. I'm teaching the trade mathematics for the trades, math 207. Apparently in the lecture notes, it shows them how to use a fucking ruler. Like in the book. I guess reading a ruler isn't all that obvious. Like the main numbers is, but like 2 and 7/16 of an inch, that's not so obvious. So teach them how to read that. See, the problem with where you're sitting, Sensi, is like there's no glare at all from this glass. See Alexia, you, and guys. So my gaze sweet, and also right where Chris is, these fucking lights get in the way. So like my gaze, people back here are hiding. Every once in a while I see them back there. But like it starts with basically here, it goes that way. And so, and you're in the center of that sweep, so you look at a lot. If you sit 2 rows back and someone sits in front of you, I'm going to stare at the other person. No, I probably knowing that now that I've brought this up, I'll still find you wherever you sit. I'll just be like, I'll only do that for a little bit, and then someone's gonna fucking say I'm being creepy, and then I gotta stop. Well, you're not falling asleep today. That's good. I'm not as. You're the one You're the guilt. I knew it was coming from somewhere. But you're not going to sleep yet. So I'm not as bad as biology. I think it's the cussing. Every once in a while I throw a cuss word in. Oh, he does?
It's the slides that.
There's not many of us that I know of that do often. Some do, but with like rare frequency, enough that when they do it, it's like, wow, watch your mouth. You know, like when grandma says it, unless grandma talks like a sailor. Or like when you hear a priest drop the F-bomb, you're like, what the, that doesn't sound right. But if someone says it all the time, it's just like, man, that's natural. If I stop saying it, if I don't cuss for the day, she'd probably ask me what's wrong.
But when Angie like texts your head and it's like, are you okay?
Right? Meets me at home with a cool wet cloth to put on my forehead.
Oh, wait, I thought you were actually good about it. She doesn't like your cussing, so don't you like try to clean up around her? Guys, you know, shut it.
I've been married for almost 19 years. I do whatever the fuck I want. I try to cuss less when there's children present.
I'm the same exact way, and my grandparents.
And when I define children, it's like the age has to have only one digit in it. Like a 10-year-old, that's fucking fair game. You hear cussing at school.
Yeah.
I know you do. I know you do. I know you've heard it from either your parents or your older brothers and sisters or the other people at school, but like, you know, a 4-year-old, I try unless it's one of my nieces or nephews. And then it's how quickly can I train them these words? Because I'm a good uncle like that. That's what uncles do. And then also get them hopped up on sugar before you send them home. That's fucking shit. No, not so much sugar that they get sick,
Okay.
but enough sugar that they won't fucking settle down the whole way.
Yeah, I had a bio teacher that used to, before you finish grandkids home, to give each one a pixie spit, like right into the tail, right before sending them back to their parents.
So that's how you do it right there. And pixie sticks are cheap and they taste good. You don't like pixie stick? What kind of candy? Do you not like candy at all? Please tell me you're one of those people.
No,
There are people like that that exist.
I just don't really strive. It has to be, I do.
Gummies work. A what?
They're clusters, you know how they have.
Oh, yeah.
How they have them in little teeny ones.
I like, I do not like the regular sweethearts that are like this. But they have chewy ones that are fucking awesome.
Oh, like the chewy street.
Yeah, they're like Chewy's free, but they're way better than Chewy's free.
Well, I like the gas station. Gas works on the back to street.
Nice.
Back when I was at it.
Oh, so it's not that you don't like candy, it's that you're trying to keep away from it.
Yes, I'm having withdrawals.
Okay, I can follow that. I feel like I've got a friend of mine, we're almost done, but this is a good story. He doesn't like hot chocolate chip cookies. He'll fucking throw them in the freezer to make them cold. I'm like, are you, what? Okay, now I'm not saying that cold chocolate chip cookies are bad. But hot chocolate chip cookies are vastly superior. And he thinks they're disgusting. He likes cold ones, but he thinks fucking hot ones with like the gooey melty chocolate. It's disgusting. It's like, I don't know how we can be friends. I just don't know. He says, and then he says, you're short. I don't know how I'm your friend, so. All right, back to work. Let's pull our sleeves up. Let's kick some ass. So we just got done talking about order of operations. Let's do some. Let's go with 12 divided by 4 plus 3 squared times 2. And I'll write my PEMDAS and cross them off as I go. There are no P's, but there is an E. So I am trying to teach you good habits, I'm gonna write down everything else first. And then do the one operation that has an exponent. 3 to the second power, or 3 squared, is another way of saying that one, is 9. And I don't see any more exponents, so that shit's done. Cross off exponents. Multiplication and division happen at the same time, so I'm gonna go left to right and do them as I see them. 12 divided by 4 is 3. And then I've got plus 9 times 2 is 18. That knocks out M and D together. Finally, addition and subtraction, there's only one. 3 plus 18 is 21. Fun, right? So much fun. Like, go home and text your friends about it. So it can be shittier. It always gets shittier. So we've got to append this. Let me write that bad boy down. I think you might find it easier if you do the writing down, put the M and D next to each other and the A and S next to each other. And even though you can't see them, when I got this big fraction bar, that is a grouping thing. So shit on the top needs to be done separately from shit on the bottom. So the way grouping symbols work means go through the rest of PEMDAS within the parentheses or within the grouping symbol. So we'll do that. So if I go through it on top, the first thing I've got on top is I have an exponent. And so 2 cubed, when it's to the third power, we say cubed, is 8. And I do not have any exponents on bottom. I can leave it alone. And I will. Let's leave it alone. And then we'll deal with the multiplication and division in them. 2 times 3 is 6. And I don't see any division. So like my first lap through, just inside the parentheses, I did the exponents. I've done the multiplication division. I now need to do the addition subtraction. So 7 plus 8 is 15, and 9 minus 6 is 3. And I've gone through the parentheses part. And now I go through the rest of it. I have no exponents. I do have division. 15 divided by 3 is 5. And we're all done, so we don't need to check for addition or subtraction. One more, just for the fun of it, where we're going to have a shitload of negative signs. Because I think it's important to talk about negative signs. Okay, remember we're doing the top separately from the bottom. Oh, let's make this cute. Let's make it more fun. Let's go with cute. You know what? Let's make the -5 squared. Let's kick that up a notch like that. Might as well go big. All right, so when we're going through it, we need to do the top and bottom separately. Addressing the exponents. The -3 cubed as it is means -3 times -3 times -3. So the rules for negatives. Two negatives make a positive. You know, like two negatives make a positive. You could either say, oh, you look really nice today, or that's an ugly blouse, you piece of shit. Like, two negatives make a positive. No, that only works in back. All right, so like these two of the negatives cancel each other out. And I'm left with one negative. So I've got 3 times 3 times 3 is 27. And then there was a negative left over inside. So I'm just doing the parentheses first. And I still have this negative out here that I'm leaving alone. The -5 squared is -5 times -5, which is positive 25. So I'll have plus 25. It's important to note the difference here with having the parentheses in. If I just had -5 squared like that, here the square is only on the 5. That is -5 times 5. That's -25. So the parentheses really matter. They're important.
So for like the person where it's like negative, parentheses -3, would it be wrong to like a negative and negative make that +3 and then?
Yes,
Okay,
because if I did it over here, if this was negative and I moved it in, this would make it positive. The answer would be positive, but the outcome should be negative. So don't move it in. If you do move it in, you have to move it in a number of times of the exponent. You have to move in 3 negatives. Don't do that. All right, this has only got, well, it's got some multiplication. Let's get the bottom caught up. 2 times -8 is -16. And then I've got a negative sign, and I've got 5 times 3 is 15. All right, again, the two negatives, there's two negatives. They cancel each other out. You can now do it when there's no exponent. And I have 27 plus 25 is 52. And -16 minus 15 is -31. And 31 is a prime number, so this does not simplify. Why did I really go over that? Because something you will do a lot of in algebra is evaluate algebraic expressions. The most frequent time you'll do this is if you're checking your work. Let's say in this example, x equals 2, y equals -1, and let's say z equals -4. And we're going to evaluate -4, x minus 2y squared minus 3z. Let's call this problem A. Good call. So what we're doing is we're just plugging in what we see. I recommend for every variable you see, you just replace it with parentheses for now. And then plug in the values 2, -1, -4. So here I've got -4 times 2. I'm going to do the parentheses first, or the exponents first. -1 squared is +1. And I have -3 times -4. -4 times 2 is -8. And then I've got -2 times 1 is -2. And I have -3 and -4. There's two negatives. So they cancel out and make it plus. 3 times 4 is 12. And then if I go left to right, -8 minus 2 would be -10. And -10 plus 12 is +2. All right, let's use those same X, Y, and Z for the next couple examples. So on B, let's do 7 minus 2 parentheses X plus Y. So the first thing we want to do is just plug in the values of X and Y before we do anything. And I'm using parentheses here. I strongly recommend you do the parentheses when you're plugging shit in. Especially if there's exponents. If there's not exponents, it's less important, but it can matter. So we follow through with order of operations. We got to do what's on the inside first. And I've got 7 minus 2. And then 2 plus -1 is +1. And then 2 times 1 is 2. So I've got 7 minus 2. And that's 5. Now, but what if I said 7 minus 2 is 5, and I did 5x plus y, and I plug that shit in, 2 plus -1, and I still get 5 times 1 is 5, and I got the same answer. Does that work? Is this valid? I got the same number. No. What if y was -2? Then the correct way would have 7 minus 2 times 2 plus -2. This is 0. 7 minus 2 times 0 is 7. But if I did this magic shit over here, if I said it was 7 minus 2 is 5, and I did 2 plus -2, I get 5 times 0 is 0. Notice that they're different answers. This up here was just coincidence. So don't think that's right. You want to do the parentheses shit first. I think the rest is just being tedious on that. Oh, well, let's, all right, now we'll skip that first. Next topic is the properties of real numbers. This is page 3. Maybe I'll start here. Start on this page because I got a lot. I don't know. I'm just going to take it on the next page. Properties of real numbers. And for this information, we're going to let A, B, and C be real numbers. Because we're going to do this in the general form. And two symbols you may have never seen before. The backwards capital E means there exists. And the upside down capital A means for all. You're really not going to give a shit about the next 15 minutes or 10 minutes. I'm going to try to go through them quickly. Most of them you already know, or what we will apply some of them. The rest of them, like the first one, you're going to be get the fuck out. But I got to show it to you because at some point, if you follow the STEM sequence, you'll be taking linear algebra and you need to see it before. So the first property is called closure. And so the way this one goes is if A and B are real, A plus B and A minus B are also real. Two is a real number, 5 is a real number, 2 plus 5 is 7, 7 is a real number. Lame. This applies to multiplication as well. So the sum or product. Sum is addition, product is multiplication. Sum or product of 2 or more real numbers is a real number. You're like, yeah, I'm not going to use that. I don't even remember that rule. I have to look at it. Someone asked me just on the street, what's the closure rule for real numbers? They're like, I don't fucking know. Go ask someone that gives a shit. But I have to teach you it. Guess what I'm not testing you on? All right, the other ones actually, the other properties show up. At least a few of them. The commutative property. Maybe I'll just stop writing the word property and just list what they are. A plus B equals B plus A. A times B equals B times A. Order doesn't matter for the sum or product of real numbers. Notice I did not say subtraction on this one, and I did not show it. Subtraction does matter. Division matters also. So this is only on addition and multiplication. The associative property. You all follow that. 2 plus 3 is the same thing as 3 plus 2. 2 times 3 is the same thing as 3 times 2. The other one that we use a lot is the associative. And that's if you've got 3 things being added together, you can add them in any order here. Like I could add A plus B first and then add C. And that's the same thing as adding B plus C first and then adding A. And this also works with multiplication. So I could basically kind of use the same wording from there here also. Doesn't matter which order I do them. The identities. So let's do the additive identity. The additive identity. There exists a real number 0. That's what it is, it's 0. Such that A plus 0 equals 0 plus A, which equals A. There's a number I can add to any number and it doesn't change the value of the number. That's the idea of identity. There's some number that I can do this operation with and it doesn't change the value. So for addition, I can add 0 to it and it doesn't change the value. I wrote this such that, and I didn't do that. There it is. The other one is called the multiplicative identity. There exists a real number. Such that, what number do I multiply by A and it doesn't change the value of A? 1. 1 times A is A times 1, which is A. So the multiplicative identity is 1. The additive identity is 0. Let's see, number 5. we've got our inverse operations. So our additive inverse and our multiplicative, that is such a fun word to try to say. The inverse, the additive inverse. The idea behind this one is a plus negative a equals 0. There's always a number to add. Real number to add. That will result in 0. And for our basic real numbers, that's the same number with the opposite sign. You're like, wow, this is fucking lame. I know 2 and negative 2 cancel each other out. Good, got it, done. When you start taking higher stuff, this comes back and it's not necessarily it's not as simple as that. By that point, you'll have already either liked mathematics and science or said, fuck that, I'm gonna go become an artist. I had someone do that. He went through physics 1 and 2 and said, nope, tap it out. The multiplicative one is not where we end up with 0, but it's where we end up with 1. So b times 1 over b equals 1. So 1 over b is the multiplicative inverse. Thank you. I did not know I was off the screen. That's pretty important information. We've got 2 more, and you'll actually use them a lot. You will use them more than any other ones that I've said so far. Oh, and I don't know which one we use more. They're that fucking important from here on out. So number 6 is the distributed property. This one will be used a lot. So distributed property. If I have some number and it's multiplied by parentheses, this is what Paxton was asking a second ago with the negative sign. Can I make it go inside and hit each of them? So the idea is doing a times b and then a times c. And if you want to check it, just pick 3 real numbers and go. Try it. You'll see that you get the same thing either way. The left side, you would normally add the insides first and then multiply. But you can multiply first and then add. That one's pretty important. And the other one that is really important, and you're gonna be like, that's fucking lame. But it's super duper important. The multiplication property of 0. Zero times a is a times 0, which is 0. You're like, what? That's lame. When you're solving equations, we rely on this property. Let's look at some examples. I have to finish part of this on you. Thursday, is that the next day? I don't even know what day it is. Tuesday right now, right? So we use a lot to simplify shit. Simplify shit with these rules. Does your bio teacher write it down? No, it just says it. There we go. You need to be exclusive. You need to be unique. So like, for example, if I've got 4 7s times 14x. The associative property says, I don't need to multiply the 14 and the x first. I can multiply the 4 7s and the 14 first. And I'm gonna make that 14 over 1. So there I use the associative identity. That sounds like some nice cold water right there. Only ice makes that sound. 14 is 7 times 2. So I can cross off this 7 and replace it with a 1. And replace that 7 with a 1. And so all I have left on bottom is 1 times 1. On top, I've got 4 times 1 times 2. And this all simplifies down to 8x. B. 5 plus 4 plus x. You would think, where does that appear? But sometimes it appears. You'll plug in like an algebraic expression and then you'll have shit that looks like this. I don't need to add the 4 and the x first. I can add the 5 and the 4 first. And I get 9 plus x. And I can use the commutative property to switch the order of these and say x plus 9, which is what we frequently do. Ideally, do put variables first, variables before constants. With addition or subtraction. Not multiplication. You don't want to say x5, you want to say 5x. And there's a reason for it. When we start using it in shapes where it matters, I'll tell you the reason. For now, just put the letters first when you have it adding them. This one kind of goes with what Paxton was asking a second ago. I've got negative m minus 4n. Fine. These are so needy. So here, I can distribute the negative sign in. This is almost like a -1 out front. That's kind of like a -1. So when I distribute it in, I've got -1 times m. And then I've got I got the minus sign, and then I've got I'll put the negative, I'll do that, minus 4n, and I'll do the times -1 right here. There we go, that doesn't make it confusing. The -1 hits both of them. And so this ends up being -1m. And I've got -1 times -4 makes it +4. And when we have numbers in front of letters like this, these are called coefficients. If the coefficient has a 1 in it, we tend to not say it. So we would write this as -m plus 4n. And it's for the same reason that we don't say 1 when we're talking generally in real life. I don't say I drove 1 car to school. That sounds stupid. I drove a car to school. I didn't eat 1 apple, I ate an apple. Right? Or if you ate more than 1 apple, that's when we start throwing the numbers in. So we tend to not use the word 1 when we're talking. About quantities of something is just implied. If you don't say the number, it's 1. Same thing with mathematics and coefficients. One more example, and then we will be done for the day. How about that? Let's go with 4x plus 20. Uh, 4 is a factor of both 4x and 20. I can pull out a 4. What I'm really doing is doing 4x divided by 4 and 20 divided by 4. And this leaves me 4 times quantity x plus 5. And like the idea of this is like, let's say x equals 2. I could have a box that's 2 wide and 4 tall, and a box that's 5 wide and 4 tall. And I'm really just doing the area. 4 times 2 is 8, and 4 times 5 is 20. The area is 28. Or I could have the 2 plus 5 first. Is 7, and then 4 times 7 is 28. We will do this distributing thing and undoing the distributing, like factoring. This is called factoring. When we put it back in, it's called distributing, but when we pull it out, it's called factoring. That becomes an important skill throughout a lot of algebra. So I brought it up here. And we will do the rest of this lecture on Thursday. Is there any questions? Did you have a good time? Was this everything that you hoped it would be? And maybe just a little bit more? You know, write in your journal how exciting this was. Does anyone journal? Every once in a while, I'll go on a journal phase. I will see you guys on Thursday. Have a good day. Yes.
So this one, do you want us to do it like that, or can like put it with or so?
No, I mean, you do not need to do the divide by 4. Okay, you can skip that side.
Okay, yeah, because I was like, could you also like do like that? Just some people side and then oh, but no, we negative.
There's no equal. There was no equal sign in the first place.
Oh, okay. So
Don't do that.
okay.
The reason why is when there's an equal, it's completely different than when there's not an equal.
Okay.
I like the question.
Okay. I was like, just because that's easier for my brain to comprehend, so that's why it automatically goes there.
Right.
Yeah, that, but now I see like it's different without that.
Right, the problem is if you leave the, put the equal in, you may not remember to take the equal out,
Oh, okay.
because there was no equal, so we're not, there was. It wasn't gonna be X equaled some number,
Oh,
and the way you were doing, you
we're
were
not
gonna end
solving
up
for
with, yeah, we
X.
weren't solving for X.
Okay, thank you.
Yes, you have the slip. Yeah. Thank you, welcome to class. She's like, I ain't coming back. Tear this shit up.
I had a question. I had to actually log in. About the My Math Lab.
Yeah.
I have to get like an access code, right? For this class.